A very good afternoon to everyone. I, Gagana S, Assistant Professor, Department of Information Science and Engineering, would like to welcome you all to the Second International Colloquium on Research Trends in Computer Science, organized by Wireless Internetworking Group, VVCE, in association with VVCE-ACM Student Chapter. Now, I would like to welcome Dr. B. Sadashive Gowda, Principal, VVCE, in his absence. I also like to welcome Dr. Ravikumar V, HOD, Department of CSE. I welcome you, sir.
Thank you.
I would also like to welcome Wing Faculty Coordinators, Dr. Gururaj Hechil and Dr. Janavi V. Welcome you, sir.
Thank you, madam.
Today, we will be having a session on role of deep learning in modern big data analytics by Dr. Nawab Muhammad Fasi Qureshi. I would now like to take this opportunity to introduce today's resource person. Dr. Nawab Muhammad Fasi Qureshi is currently working as Assistant Professor in the Department of Computer Education, Sungkyunkwan University, Seoul, Korea. He completed his Bachelor of Engineering in Software Engineering, Master of Engineering in Information Technology from Mehran University of Engineering and Technology, Pakistan. And he completed his Doctor of Philosophy in Computer Engineering from Sungkyunkwan University, South Korea. His research interests are in the field of big data analytics, IoT-enabled context-aware data processing, cloud computing, artificial intelligence, machine learning, and deep learning. He has received first Superior Research Award for the best thesis and research performance from College of Information and Communication Engineering. He is also awarded with Brain Korea Postdoctoral Fellowship in 2017. He is the lead guest editor of Role of Deep Learning Models and Analytics in an Industrial Multimedia Environment. He has published papers in various conferences and international journals. He has also published a book chapter. We are very fortunate to have you with us, sir. A hearty welcome to you. And over to you, sir.
Thank you very much for your brief introduction. First of all, I would like to thank VVC management, specifically the principal, HOD, Professor Ravi and Professor Guru, and the wing coordinator. The topic which I'm today discussing is modern trends in deep learning. And in this topic, we are going to discuss and learn what are different deep learning models, how do we understand them, what is the basic point of understanding. In research world, we discuss so much about deep learning. So what are the basic things about the deep learning? And from the basic start towards developing a singular level model, we are going to learn and discuss about it. Before I start about the discussion about the modern trends in deep learning, let me formally discuss about my university. As you have heard about the SKKU, the Sungkyunkwan University, from the announcing doctor, that this is an old university, one of the old universities of South Korea. And it was built around 1398. That's so long. And probably we may be knowing that there are only few institutes which are that much old. And after that, there were so many reforms by the South Koreans, and they took it at a very advanced level. And they came up with a strategy to open up the university in 1946. And the most interesting thing about Sungkyunkwan University is it has got very strong tie-ups with the Samsung, that you may say a large portion of Samsung projects, and the coordinations are with the Sungkyunkwan University. Specifically, if we talk about the artificial intelligence, deep learning, and semiconductor, as well as the chemical section. So you may say that since the beginning of 1996 partnership with the Samsung, that is the headquarter having in Korea, it has been progressing well. And now we see in 2020 as well as in 2021 that it is one of the progressive and innovative universities in South Korea. Let me talk a little bit more about the SKKU. It has got two campuses. The first one is humanities and social sciences, and the second one is a natural science. In humanities and social science, we have business, economics, and social science related disciplines. And in the natural science campus, it is broadly comprising of the engineering departments, the nanomaterial sciences, chemical, more specifically artificial intelligence, and recently we have introduced the super sapient department. That is precisely the whole of the department consists of the artificial intelligence workflow. In addition to that, a little bit more that our university has got a robust reputation out there in the market. If you talk about the domestic rankings, it is the first private university in South Korea that is the number one, you may say, although there are so many institutes, but specifically if we talk about the domestic universities, it comes in top 5 in all over, but in private universities, it is the leading one. And of course, it is one of the leading universities in terms of the employment. International ranking, if we talk about, you may search on QS ranking. It has got a robust ranking. It ranks around averagely 88 rank. If we talk about the world ranking in THE, that is 81, between 81 and 90. It comprises, it varies every year. It has got a kind of an average ranking count. So, and if we talk about international ranking impact, so it's on the 30th ranking and all over the world. And if we talk about the most innovative university, so it has got the rank of the 45th according to the Reuters. Now let's talk about today's topic of discussion. Before I start the discussion, I'm very much thankful to Professor Dr. Guru, and he invited me for this Second International Colloquium on recent trends in computer science. And there, we have a lot of basic as well as the advanced related materials, and we are working on the real-time environmental modules as well as the structure. So it's very judging to fix up some criteria on presenting some topic. So I tried to choose a topic that is discussing the basics, and it will be a good contribution to the related audience so that they may be knowing well that what exactly is deep learning, how do we know the deep learning in terms of AI branch as well as the machine learning branch, how it has got an extension from the machine learning basic criteria. So let me formally start the discussion with the machine learning basics. In the machine learning, what do? We label the data and then ask the machine to understand that labeled data and then execute different kinds of the model. And this labeling data consists of two stages. The first one is a training part. The second one is a prediction part. So in a way, you may say that if you want a machine to work according to your desire or requirement, then at first you need to train it, and then you go for any kind of query-related mechanism that we may say as a prediction model. So according to this slide, we see that we have the labeling data, and then we go for different machine learning models. That's the training part. And once the machine is mature enough to get trained, then we go for asking the answers from the machine. So that is a part of the prediction, and then we give a kind of the random data, and then we evaluate the machine from the learning models, and then precisely we get our answer in the form of the prediction. Now, there are different types of the learnings here, because we know that we have to deal with different kinds of the problems. What are the problem criterias? We have the supervised learning, we have the unsupervised learning, we have the reinforcement learning. Now, how do we understand these different types and formats of these learnings? Because these are the essence, and from that part we could be understanding more clearly that how do we see the deep learning perspective that is derived from the machine learning. So in the supervised learning, we know many things. Let me discuss it in a very basic general profile that the audience may understand it very well, that we have different already known input data that we may say is a kind of a labeled training data, and the machines are much more aware about them. So in that context, we classify them, we retrieve our answers, and many of the things are already known. So it's not a kind of complex criteria for different clusters to retrieve different answers. But when we talk about unsupervised learning, that says different kind of the unknown entities. So in that context, we see that we have to make a machine aware about different data stuff. So what do we do? Now the remedy is we formulate a cluster, and in that cluster we draw some boundaries, and then we classify that particular area and then give them the meanings in the form of the patterns, and those patterns are basically identified by the machines. So that is named as the unsupervised learning. And then we have got reinforcement learning. Now in the reinforcement learning, there are so many definitions, but if we just have to take a simple example, so you may see that many of you are observing at your homes that the kids are playing video games. Since the beginning of the video games, if you just tackle up the example of the Atari game, now that's the best example for the reinforcement learning. So according to that, an act is to be performed based on the feedback. That is, whatsoever is the action, the reaction is based on according to that action. So if we say that the basic Atari game or pinball game or simple games which were back at their Atari time, those are the reinforcement learning example. We would not be wrong on those are the simple examples, right? Now, how do we involve different kinds of learning types here? So at first we have different data entities. Let's say here we have a text document, and then we have different classes of those documents based upon their classification, such as labeled, unlabeled, and then we perform different kinds of the formulation methods, such as here in this case, regression process, and then we formulate the result in different clusters. Now the question would be, why do we go for different clustering? So in the clusters, we identify different boundaries and then fix up the different parameters, and then it's more easy for us to formulate the boundary-based answers. Now, that was a little bit brief. Now, how do we relate machine learning with deep learning? Because it's very important to understand. Many of us have got different concepts, and some might, if not, they are not well aware about it. So some might also be confusing the machine learning with the deep learning aspect. So in that case, we need to learn and fix up few things very straight. That is, methods work before human design representation, and ML that we are talking about is just working on the optimizing ways to make a fit prediction. Like here, if we observe this diagram, so it's ML in practice, and here what do we have? We have different kinds of the data with feature that computers can understand and then perform different kind of the algorithms. Now, what kind of different activities are to be applied or performed from that part is different features, such as in case of the text document, we have different words, how to identify the current per scenario, what are different positions in the text documents, how to go for a simple text content. So different size of the document, so many things are there. So in that way, our algorithm is basically focusing on different weights and retrieving those results back. But if we are more closely watching the comparison, so what would be that specific comparison? That is a machine learning subfield of learning, representation of data, that is leading towards the learning patterns. And when we precisely focus on the deep learning, then what do we come up with? Multiple levels. Now, this could be a kind of one identifiable scenario and perspective that there we go for different kinds of the fields and focus on the data. But here we have got different kinds of the levels. Now in those levels, what do we have? We have different kinds of the multiple layers. So layer by layer, we identify and formulate different kinds of the data queries. If you find the system tons of information, it begins to understand and respond it in a useful way. Now, what do we mean by tons of information? In machine learning, when we give different kinds of classification data points, then we may not be going into deep down. But when we talk about layer by layer, that means if you take a simple image and then you dig out different details of that image, and then you again dig out in that specific portion or point to go for different coloring schemes or different kind of the formulations, then it works like a layer by layer. Now here, if we observe the different comparison, what do we see? We have a input data, and that data is to be processed according to the feature extraction. And in that feature extraction, now further it is classified according to those data points. And then we get a kind of an output in terms of maybe it's a car or maybe it's not a car. But when you talk about the deep learning, then what do we see? We observe a combination of feature extraction and classification all together. Now this combination is processing at the same time. So in that way, we need a kind of more robust scenario where both the things would be working together. Now, the result would again certainly be car or no car, but the difference is here, if you closely observe, the feature extraction and classification are working together. That means a much more deep and detailed result workflow would be there. Now the question is, how useful is deep learning? So many design features such as overspecified, incomplete, and long-taking design validations, they would be creating different kinds of the troubles. And would it be easy? Is it flexible? Is it adoptable? Does it require different kinds of the heavy equipment, or would it be easy for anyone to execute different kinds of the models? So that is basically the useful criteria. And moreover, we may see that is it flexible to be adopted universally, or different kinds of the mechanisms are there where they would be limiting the utilization, or the architectures are different. So based on that, we may be evaluating different usefulness criteria. So in that context, what do we see? We have a graph from the Google Trends, and there we see that since from the beginning, it was not having that much scope. And after that, after 2015, it got a good height, and ultimately took a good lead. Now, what are the possible point of understandings here that help deep learning to take a good lead? So the answer is, if we go for the deep complex solution problems and their solutions, then ML may not be helping much. And ML has got different limitations. ML would be extracting different kinds of the features and applying different models, but precisely that has got different limitations. For example, if we talk about NLP, that is natural language processing. So certainly ML would dig down different kinds of the problems which would be sorted out by the ML. But if we have to go deep down, if you have to extract out different kinds of the graphical as well as numerical analytics, then DL is more useful. Now let's talk about the different basic point of understanding for utilizing the deep learning. So here we have got the image classification. Now in this image classification, what do we have? We have a core task in the computer vision. And in that core task, what do we need to do? We need to identify, is it a cat or any other kind of the object? Because as being a human, we may be knowing it very well through our eyes that what specifically is this object, but for a machine, it's not easy to understand until and unless different kinds of the criterias are to be adopted, such as what are different dynamics, the typical structuring of the images. So after that, it will be in a more flexible way, in a more good way to identify the things. So here, we may need to assume the data point, that is it a dog, is it a cat, truck, or plane, or so on. So let's just assume that, okay, we need to find this object as it is a cat. So how do we need to find? Now what the computer sees, if you just spectacle up a single kind of the image and then perform different kind of the analytics, there's a lot of data, only data. So for computer, lots of numerical data that is precisely closed in the matrix format, and what a computer would be observing. So in that way, the image is to be more analyzed. The image requires different kind of the analytics, that what is the different kind of the color, and how are different dynamics, are they straight or maybe having different kind of the variations in terms of their graphical structures. So that is again a problem, a semantic gap that highly likely it's very difficult to identify with the help of the ML. And then the second challenge, that is the viewpoint variation, that how a different kind of the viewpoints would be. For example, if you just observe the same image, now you may be having a different good variety of data from a computer point of view, but when we talk about the angular point of view, that how this angle is to be observed. So in that way, we see that again, even the humans may also make mistake if there are not proper angular formats. So all pixels change when the camera moves, the data moves, and precisely the whole of the situation moves. Another challenge. Third one is illumination. What are the different illuminated scenarios that are, if you consider the same cat or maybe an image of the cat, and then you find it in a different situations, that is, if we take up the first picture diagram, the image, then the computer will be judging it in a different way. The second one, totally in a different position, highly likely not easy to identify. Third one, maybe the cat is trying to think something, or maybe observing something, a kind of a different image set. And fourth one, very difficult. Is it a panther? Is it a tiger? Is it a cat? Not easy, a kind of a complex challenge. And then the deformation. Now in the deformation, what do we see? We see a different, another kind of a complex situation where even though you know that the object is known for a system or a machine, but the criteria is different to judge. Likewise, if we observe here at the left side, the first picture diagram, what do we see? We need to be more careful to identify, is it a cat or maybe it could be a panther, right? The second image, a very cute act by a cat, but again, it is challenging deformation. Third one, a very petty kind of an attitude. Another deformation. Fourth one, again, the fourth challenge, another deformation. So it's very complex situation to identify a variety of stuff. Now, just imagine that if you are going to identify the situation from just a human eye, or maybe using different street models of the ML, what you are going to do is maybe identifying a different object. For example, if you take a simple computer vision algorithms which are not involving the deep learning, then highly likely it will be identifying different objects for animal scenarios than the cats. And then occlusion. Now, even though in this situation, how we may be confirming that it is a cat? Specifically, okay, if we talk about the first image that looks reasonable, maybe if we focus a little, but in the second perspective, not, highly likely not. It's very difficult to identify the exact image. And in the third part, although we are very much familiar with the color combinations of the cat as well as the typical structure, but even though if we do not consider these kind of the parameters, then it's very difficult that, okay, maybe a kind of the cat toy is there, not a real cat, right? Likewise, the things. And then the background clutter. Now here in this background clutter part, at the left side, if you look upon at a little distance, not easy. Highly likely you will not be able, we all not be able to judge the situation, that how it may be analyzed that a typical cat image is there. And at the right side, again, very difficult. So because of the background clutters, the image is not typically in a shape that may be reflecting a very clear feature extractions. For example, let's use here the computer vision algorithms to identify different kinds of the boundaries. Now, the right side, if we take up this white background based cat image, the computer vision algorithm will fail, straight away fail. And then intra-class variation. So which one is what? And then if we need to make more classification in more depth and detail, then it would again be very, very much difficult in terms of their positions, in terms of their coloring, as well as different kinds of related classification. So for that, what do we see? We see linear classification, that how do we formulate different kinds of images? We take up different data sets, and CIFAR10 is a kind of a very known, popular mechanism that help us to identify different kinds of the objects. And this formulation works in the same way, just like there is a training data, and then we have the test image data. So as discussed in the previous slide, the training data helps us to understand and evaluate different kinds of the dynamics, such as what are the typical size of the diagram or the picture, what are different dynamics of that object, how they are classified, how they are read well, what are different kind of the multi-layer mechanisms which are identifying them. So based upon all that complex multi-layered architecture, then the system becomes ready to identify the diagrams or the pictures, and then we go for different kind of the test images. So based upon those already of system aware knowledge, that data is to be analyzed. Like now, how this thing is happening in the technical order. So if we talk about the parameter approach, we have got an image, and then the system needs to identify the different parameters. Just like here, we have 32 by 32 by 33 numbers. In total, we have 3072. Now, these things are to be passed on by a function that will evaluate the different codings. What are the typical formulations here? These are responsible to identify the weights. What are the weights we are going to talk, and then the values which are the image. Just like here, these are the numbers, so we put up these values and then we apply the weights, and then we get the score, that what is the close variation score to identify different kind of the objects. So that is how it is matching a typical diagram or the object. Now here, if we extend this classifier, so we have a function that has got the image parameters and then the weight, and then we formulate this multiplication. Now this is a part of the system process, so we need to tackle up these scores and values, and then once they are done, then we need to add on the B, that is having a score balance to this linear classification. So through this point, we get a conclusive value for that typical image. Now, if we take upon the example with the 4 pixel and 3 classes, so how this thing happened. Now, before we go for these pixels and classes, how do we identify these pixel and classes? For example, if we have an image, now what we need to do is we need to identify different pixel points, and then based on that, we have to give up different positions. And then we need to again classify the entities, such as either it is a cat, either it is a dog, or it is a ship. Now these cat, dog, or ship are comprises of a class. So in a way, you may say that if you have to identify an object, and then you need to give a group of input, that what kind of object is it. So that would be the number of the classes. So as much as the different variety of the object would be, that much would be the number of the classes. Now these classes will play a typical role, that is to input the matching score between the calculated score to identify a close variance. So in that way, it will be helpful to identify that typical image. For example, here we see that straight pixels into the columns, and then we calculate different weights and then apply them with the function, and then retrieve the results. And based on that typical score variation, we get the answer for that typical input image. Now, if we go for more viewpoint details, then what do we have got? We have this algebraic view, and then we expand the results according to these different classes as discussed, so that we may be knowing that what are the close variations, how the images are working, and how they are retrieving the answers based on that typical function. So hopefully this is now clear that when we formulate a different image that is either a part or not a part of the system, and now we need to process that image through a system by giving different classes, then how the system concludes that what kind of the image is it. Now these things are not that much simple. This is just a single point of view. So we need to add on different more complex. For example, this is a linear classifier, and in this linear classifier, it is very much straight, very simple thing in this field of deep learning to identify different image values and entities. Moreover, geometric point of view. So in this geometric point of view, we have different situations, such as in this geometric point of view here, we have to draw the dynamics, that what kind of the classifications are we after, right? So in these dynamic classifications, we need to draw the boundaries, that, okay, we need to give that much number of the classes, and according to that much number of classes, we need to explicitly draw the areas that which one is more close. And based on this geometric point of view, that typical portion or the selection is to be selected, and then it has to be matched. And then we get the answer according to the linear classification, because it is again still very simple and straight, but now it has got an expansion of the areas so that we may match the more related area. Now, hard cases. What are typical hard cases? So if we talk about classes, the first and third quads, right? And the second and fourth quad are related classes. But if we talk about the class 1 and class 2 in this part, so now we have got a little variation. So the straight diagrams or straight executions with respect to the linear classifiers are a little bit simpler. But when we talk about a complex thing that is either involving a different variating image within the image or having multiple images, just as in the third part. So the situation varies. For example, class 1, and here we have got norm that is varying between values, and class 2, it is consisting of everything, right? In the same way, if we talk about the third case, 3 modes involving in the typical image having a different linear classifier. So it will be having a little bit more complex situation to identify the things. So if we take these cases as a hard cases, we may be knowing very well that how the linear classifiers are to be operating in different situations. Now, you may consider this same situation as a case study and apply or incorporate in a different variety of images to identify these linear classifiers. So again, let's summarize this 3 point of views. We have the algebraic point of view, we have the visual point of view, we have the graphical, sorry, not graphical, but geometric point of view. And combinedly, they are working in a different layering situations. So hopefully now we are very much clear about the formation and working of the deep learning at a very basic layer. That's a linear classification. Now, deep learning attracts lots of attention. Why it is attracting lots of attention, we most of us know. And for some of the students who are only working with the machine learning or maybe reluctant to work on deep learning models because of different kinds of GPU utilization. I'm going to talk about the GPU utilization. Then we need to see that it has got a huge charm, and there are so many in-depth complex scenarios could be easily sorted out by the deep learning model. Now, how the deep learning is related to the human brain learning. So most of us know about this basic part of the AI that is related to the CNN. And again, CNN is a close collaborator of the deep learning. So we know that in human brain, we have typical neurons. These neurons exchange different kinds of the signals, and they find a structure called the dendrites. They help to exchange the different signals. And then we have the spikes of electrical activities, which are known with the axons, that eventually split different kinds of the branches so that the current may pass on to different neurons. And at the end of each branch, a structure that is synapses converts the activity from axon and process different connected neurons all together. So in a way, you may say that even the human brain works on different electrical spikes, electrical signal process, you may say, right? So now the same situation is very much helpful, and it will not be wrong if we say that scientists or researchers have closely studied this concept well, and they came up with this idea to execute and utilize this neural network, or not neural network, human neural network scenario to be utilizing in the deep learning scenario. So before we move ahead with the connection of CNN or maybe neural network or maybe neuron with the deep learning, we need to understand that how this neuron is basically processing a huge, large data set. So here we see that a neuron that is taking different input, and then performing that input according to the execution of the electrical activity in the axon, and then later it is influencing a neuron to utilize that knowledge. Now, let me summarize it in a simple way. For example, if a kind of a thought is coming in your mind and then it is leading towards another thinking, and then you are having a different multiple branches of the thinking, it's a kind of an expansion. So think like that, it is a connected execution of multiple neurons, and which are passing the knowledge from one neuron to another neuron. So that is how this thinking is going on, and you are having a variation in your ideas. So this, you may say, is a neural network that is processing different collaborative data, and then the scientists have long ago formulated different simulated programs regarding the neural networks, which are still helping us, and certainly they will help us in future as well to formulate more complex situations. Now, a simple neuron that consists of a body and that has got some input and that has got some output, and what this neuron is doing, either it is being utilized or it is teaching. So a neuron, that is artificial neuron, in our case, is a device with many inputs and one output. Now, why do we say many input and one output? Why not many input and many output? Why not one input and many output? Although we are processing some kind of the data. So a neuron has to pass the information as an output in terms of zeros or one, and that has to be unique, because if it is passing multiple knowledge factors, then it will confuse the other neuron, and highly likely it will confuse the whole of the model. So thinking must be straight or in zeros and one, so that it would be much more productive and useful for the other entity. Okay, a little detail about the simple neuron execution. So we have the training modes, we have the firing rules. Now, if you study and read all these details, you come up with a simple idea that at first, a human brain also requires a training, and then it has to go for some kind of the test. Likewise, if we take the exam, so prior to exam of any course or maybe any topic, we need to go for some kind of the training, and that training help us to prepare the examination process. The same thing happens here, that we have got the training mode, and the training mode, we process different data, we digest different data in the neural network, and after that we process those patterns. So if the input data does not belong in the taught list, that is a kind of a new entity, the firing rule is used to determine whether to fire or not. Now, here comes the interesting part, that it's a kind of a new remedy, that if some kind of the knowledge is not in front of a neuron, then how it has to behave. So it will utilize the different learned training modes and then perform the firing rule. Now, what is inside this firing rule? It is the concept, count, and determines how one calculates whether a neuron fires for any kind of the input. So it is based on different kinds of the behavior. Now, let's not just mix up this study with the neuroscience, of course, but every neuron behaves differently for the same thing, just like every human has a different kind of the reaction. So accordingly, the behaviors are different, the responses are different. So this firing rule is basically determining that whenever kind of an unknown data appears, so how the neuron has to behave. Now, you may closely relate this thing with the kind of any kind of the psychological patient, or maybe anxiety or depression kind of the patient, that whenever some kind of the uncertain data is in front of them, then how they are going to behave. Now, that's very complex and unpredictable. So let's just skip up that part and get back to the deep learning study. Now, here we have got an example application. And in this example application, we have the handwriting digital recognition. And this you may see as a kind of the image. But we need to be more rigorous in the process, that is to identify the detail points. So in the machine, it will just be reflecting the digit 2, but how this has to identify all these things. So according to the deep learning digital dynamical part, if we have the input image data, and now what do? We will apply different kind of the pixels here. So the pixel information is to be collected. Now here, if you closely observe this image has got different kinds of the pixel definition or the values, and they are precisely consisting of the values according to the size of the image, such as here we have got 16 by 16, so in total we will be having 256. And now each of the pixel is to be determined how and what kind of the size is the pixel acquiring. So we may say if it is having kind of an ink position or maybe the specification of any kind of the data, then it leads to the 1. If it has got no ink or no data, then it will ultimately be leading to 0. So precisely we calculate the output according to our previous understood model, and then we see that okay, we have got the scores and what are different scores which are variating to each other, and then we come up with the simple output. More detail if we need to go for, then what do we need to do is we need to tackle up the same information, process it in the machine, but this time we need to see that we know that deep learning is utilizing a function that is closely related, associated with the neural network. Now, let's just combine both the knowledge factors, the neural network discussion, which we discussed, the machine learning basic part, which differentiate between the machine learning and deep learning, and then the basic parts of the deep learning, which help us to formulate a problem. So combine them all together, and then we come up that how we are going to understand and analyze a typical image, fetch different kind of the values, and then process them, align them together. Now the backside, in the calculation part, what do we see? A neuron that is processing and performing different tasks. It has got different pixel values. It has got the image values as in comparison or in collaboration with the neural network entities, which we just discussed. And then we have an equation that resolve the problem. How it is resolving the problem? It is fetching out the results based on that activation function, and ultimately that is giving us the typical score value, that how close the variation is, and how we may relate that typical activity to that typical neuron. Now, this is a simple concept. Now combine all these concepts together. And when you just combine all these functionalities of a typical neural network having these simple, straight, linear functionality, combine them, how you are going to combine them in the multiple layers. So here we have the input. That's the input layer that consists of the huge workload of the input pixels along with the weight. And then we have this layer, this layering part. They are closely connected together, just like the neurons are connected in our brain. Millions and billions of neurons are closely connected through their connections, weight. And then these neurons are collaborating to each other. So the part which is hidden, these are the hidden layers that precisely formulate different operations all together and come up with a conclusion. Now, let me make it more simplified. That again, take a same example of thinking. For example, if you are thinking for some idea, any kind of the problem, maybe you are looking after for some research problem, or you are heading towards you are facing a problem in your research and you want to identify the solution. So what would be the way? The way would be to keeping the training data in consideration in your mind, that what are different already solutions available, and then what are the things which are left over that are not to be considered, which are never observed, or maybe the observation is not according to your own situation. So we combine them all together. The mind is thinking, and it is making us so many ways out. We have to choose one way, and precisely we lead towards the output. So the same thing is happening here, but deep means many hidden layers. So all of the things are working all together, and then we are retrieving the result as an output. Now, precisely if we talk about a simple neural network example, so what do we have? What is exactly happening? We are processing different data entities through those neurons, processing the functions, and here in this case we have the sigmoid function, and that is processing the data entities according to their weights and their input value, and as it is consisting of multiple executions. So you may see that the resultant data points are to be exchanged further as an input. So input to output to input to output, this kind of the workflow is observed here, just like here. So based upon these calculations, the neurons are further processing and proceeding their activities and leading towards the single point conclusion. Different parameters define different functions. So now just following the same remedy as we discussed, that if you are after some kind of the problem and looking after some solution, so at the same time you will be having the multi-directional or multiple ideas to solve a different criteria, but at the same time you need to be focused and you need to stay alert to process these data points, because a simple straight logical answer will lead you to a conclusion, a fruitful conclusion, and a kind of ambiguous idea that has got no functional reality may not lead to the fruitful conclusion. So likewise here, when we process different kinds of the data entities in the functions using these metric operations, then we need to focus that what are typical layering neurons that are processing different data points and which are required, which are not required. So we need to be focused on that part and precisely observe those calculations. And here we have the metric operation. Now we know about this metric operation. We need to apply and perform different kinds of the calculations. So again, with this same operation, we take the help and exchange the data points. These are different data points you would be highly likely observing. And based on these data points, we perform the calculations to lead towards the functional result. So in this way, we see that multiple linear functions work together, or non-linear functions may also be the part, depends on the situation. But according to this discussion part, we see that we have different kinds of the sigmoid layers, functional layers, which are processing different data and exchanging different points, and even they are exchanging the different data entities between each other to a fruitful conclusion. So all these things are happening in parallel, and utilizing this speed up metrics operation so that things could be analyzed well. For example, if you are thinking for some idea, we are taking the same idea because this will help us to understand the different scenarios and situation. That if you have to identify some solution, what you need to do is you need to think parallel. Now, our mind, even the computer, technically, if we talk about, then the parallelism is very complex situation that involves different kinds of the processing computation. For example, if you've got a simple processor, then it's highly likely possible when you talk about parallelism. That means you need to figure out different computation percentiles that are assigned to individual process. For example, process 1, 33%, process 2, 33%, process 3, 33.4%, and precisely in that way you may make a parallelism. So in the same way, we apply different sigmoid functions all together to reach out to this parallelism, and of course we need equipment for that. Without equipment, practically it is not possible. You may go for different kind of the simulation, keeping up different simulation parameters, but if you have to utilize them in the real sense, then you need a good equipment. And then we see the SoftMax layer. Now these layers are different functional parameters that process the sigmoid functions, and you involve different kinds of the operations there. For example, here, in general, the output network could be a value, and it may not be easy to interpret, so we process them in different kind of the layer. We even name these layers. Sometimes they're having a simple sigmoid function, some kind they are having a complex sigmoid function. So here, in this way, as we have a SoftMax layer executing and processing different values, then what do we need to see? We need to see different kinds of the functionalities. That is how the input value that is processing the neural data, and these neural data points are further dividing each other to get the result set. And let's just not forget that it has got a huge role of the probability, and that probability eventually help us to identify the similarity and the variations. How to set network parameters? Now, these network parameters are a very useful entity, and if we do not set them, then eventually we may distract our goal, right? So taking the same scenario from the example part, now what do we have? We have the different dynamics, we have the ink and knowing parameters, and then we process them in those models, having the parallel solution formations, applying the SoftMax as discussed, and then what do? We apply different parameters that has got different values. For example, here, yes. So here we have got different input values. Now image 1, image 2. So these have different values accordingly, right? So it may not be a kind of a fixed situation. So we need to fix up the parameters to identify and grab those values, cache them, and make the related score equalization, so that we will be in a good position to identify the image in a more robust way. So this network parameters help us to resolve these things. Now, more importantly, the training data part is there. I think I need to be rushed because I have to cover up a few more things. Anyways, so let me go through the things, and if there is some kind of a requirement to talk about in more detail, then I'll focus on that part. So now here comes the interesting part, the training data. Now in this training data point, what do we have to do is we have different kinds of the images and their labels. But if we talk about the deep learning situation, then we need to focus on the training part as well as the network parameters to judge them more accurately than as compared to the machine learning part. So that consists of a scenario that is named as a cost. Now in this cost part, we need to calculate different kind of the cost values, such as a set of network parameters. Each parameter has different cost. Here we have got one that has got a cost, right? So all these costs are equated and calculated based upon these deep learning models, and then we formulate the net total cost. So based on a single image, we may be calculating a cost as a group cost, but for a group of images, we need to go for the a more detailed cost. We are going to talk about that part. So in this cost, what exactly is a cost? The cost is basically describing different values which are to be matched with the target set. So in the target set, we need to keep a comparison that did we achieve a typical cost according to that level or not? If we get that typical cost, then we would be in a good position to match up that criteria. So the cost is calculated. If it is calculated, then it would be having a win-win situation. If not, then it may be skipping the part. And yes, of course, we know that the cost is to be evaluated by a typical function. Now, as I discussed in the last slide, that we need to go for the total cost. So as we are training different parts, so we need to train different element of and the values of the images, and each of that image is comprising of the cost. So accordingly, we have to calculate all these costs. And we have the formula to calculate all these costs that works well with the summation. How bad the network parameters is on this task. So to find that, we need to focus on the cost parameter that minimizes the value. In that way, we will be in a position to compare different activities. And then we have the gradient descent error surface. That is again more a kind of an important perspective that evaluate different parameters according to their weights. We've got different scenarios. Based on that, we apply these parameters of the gradient descent to evaluate these cost factors, how they are randomly picked, how they are giving different kind of the cost factors. Is it negating? It is not negating, right? So different situations are there. And more importantly, they give us a sense of the execution in time-based learning. So this is a gradient cost execution. And then after that, we have the local minima. That is the gradient descent that never guarantees global minima. So for that, we need to find a different initial point that reach out to different minima. So different kind of the results are to be retrieved, right? In that context, we have local minima. Beside local minima, we have the cost variation. That is how it has to stack up. Like here, if we have observed that it is stuck up at a local minima, then what are the criteria, how the function is behaving, what are different values at the specific point of the stacks. Now, these all parameters, they are helpful in evaluating the positions of the execution. And then we have different batches to execute different images. That is, if we have if we can group up different images all together, then we would be in a good position to idealize. For example, if you have 10 images all together, but no, you don't want to evaluate all the 10 images all together. What you want the individual image, but within a group, so that maybe 2 or 3 or 4, it may be related, it may not be related. Or there is one more situation. In this case, as we have 0 and 1, so in terms of 0 and 1, you will be highly likely in a more good position to identify only yes or no kind of the situation. So these batch situations will help us. And the purpose of the batch is also to exclusively identify the related things to be compared from. And then we have the back propagation. Now, this back propagation concept is a kind of the same thing which we used to learn and discuss in AI and ML, and networks have different parameters. So in that way, we see that back propagation is a way to compute, but not today. Many tools are available that compute the gradient automatically. So in these days, we have different kinds of softwares, frameworks available. Dino, TensorFlow, Charge, and there are many, many more these days. With the passage of time, according to the situation, based upon the complex problem or the simplicity, the different kind of the frameworks are there. You may utilize them to execute these different default executions. You can also program your own add-ons in the frameworks. I will not suggest to go for a complete creation of the framework. It's a complex task. It requires workforce. It requires a kind of a group collaboration. But if you are individual, you want to utilize all these functions, you can deploy these frameworks. Size of data set, again, an important perspective. For example, if you are comparing, equating, calculating all these things all together, then size again matters. Because if that size example is exceeding according to the calculated rule, just like mentioned here, then you may expect some issues. And then we have the training backprop algorithms. Now these algorithms help us to train the network in a much more robust way. That is, if we talk about the forward pass, now this forward pass is basically focusing on each of the neuron. And you may say it's a kind of a fine-grained filtering kind of a technique in the backprop algorithm that is specifically searching weight values to minimize different kinds of the errors. And then this backward pass, it's collecting a kind of a group layered workings and updating the typical error points in a recursive order so that it may reduce different kind of the issues. And after that, we have the backpropagation. These things are very much similar, which we already know regarding the AI and the typical machine learning scenarios. So what we have to do is, in terms of machine learning, when we consider the nodes and when we consider the functional operations, now here, what do we consider? The same concept of backpropagation, but this time here in the neural network with the neuron, specifically carrying the value of the neuron, having the weights, and then we go for the forward step, and then if in case of the error propagation, the backward step. Now, this is a kind of typical model, and here we see that in order to retrieve a good result, then what we have to do is we have to go for a good GPU. Now, what is a simple GPU? It's a typical device that works in collaboration with your CPU, but more precisely, it helps you to execute different kinds of the parallel tasks altogether. And this eventually help you to go for the real-time executions. So we have this NVIDIA, and there are so many other GPU, you may say, companies, and so eventually they help you to figure out the solution in a much more robust way as compared to a simple normal CPU operation. Okay, I think I was given 1 hour time, so maybe I maybe skip up this part because it consists of the whole workflow of this CNN model. It's a kind of a brief thing, but we may not be finishing up it. Okay, thank you, everybody, and please feel free to ask any kind of the question which we discuss, any kind of a question from the content which we discuss.
Thank you so much for the informative session, sir. We have a question from one of the participants.
Oh, can I close this sharing because I'm not able to watch any kind of audience or maybe the members. Is it okay?
Okay, you can close.
Okay.
Sir, the question is, what is a predictive maintenance?
Sorry. Can you paste the questions in the comments, maybe?
Yes,
okay,
sir.
So we have the comments. We have the comments. Okay. Yes, we have predictive maintenance. Now, what happens when we perform some kind of the prediction? So, in the prediction format, we need to take care about the training data, the data set which we discussed in detail, that how this training part is very important, and then accordingly we perform a typical prediction. So, if we have to understand the predictive maintenance, that means something which has to be in place. Now, when we talk about in place, that means some kind of a prediction is carrying on, and then it is identifying the issues, and at the same time, it is addressing the errors. So, uh, uh, just to be a little brief, predictive maintenance is making the maintenance in a runtime prediction. Yes.
Sir, the next question is, which network is best to be used to minimize errors, ANN or CNN?
You may say that, sorry, because of the time situation, we couldn't discuss the CNN in much more detail, although it was in my plan at least. I included the slides to discuss them in much more detail. What happened that in the artificial neural network, that is ANN, you have a little subsidiaries which are to be incorporated in the convolutional neural network, because in the convolutional neural network you have to utilize multiple hidden layers altogether, and again those are also working behind the neurons, but as a part of the neuron that is precisely processing a singular data, the same thing is to be happening with the help of the convolutional neural network. So in a way, if you need to judge that what is the best to use according to the errors, ANN will be more filtering as compared to CNN. But if you have got a good computation power, if you are having a good system to filter out things, then CNN will not make you feel like so.
The next question is, where will we get the real-time data? Please specify the website name.
Okay. Now this is a kind of a tricky question. Maybe let me give you some hint or idea, because what happened? You have Kaggle, and you find some data points, but the data is again categorized into formats. The first one is synthetic data. The second one is real-time data. Now, if you want the real-time data, then we have few sources, such as we have IoT devices which are continuously sensing the data part, and eventually delivering us the real time thing. But when we talk about the synthetic data is also generating some real time data, but that is not close to the reality. So uh, uh, it's very hard to say that where you will find the real-time data, because many of the companies disclose their data according to their license system, and but highly likely you will find some data thing in on the Kaggle.
The next question is, where we implement deep learning, on structured data or unstructured data?
Uh, Deep learning, in order to answer this thing, we need to be very much clear that why do we need to go for the deep learning. For example, we discussed about the training data. Training is required everywhere. For example, if you observe a small child uh, that do not know how to walk, and then you ask that child to run, it's not possible, right? So in the same way, we have different data patterns: structured data, unstructured data. If you talk about the big data, that is closely working for the unstructured data rather the structured data, because the data flow is continuously coming, and you are not having any time to make the structural bounds, right? So uh, we may implement the deep learning in both the perspective, but it depends on the complexity. If the complexity is not that much high, and the equipment is also facilitating, then okay. If not, then it will be troubling.
Okay, sir. Thank you so much.
Thank you very
Thank you
much.
so much for your valuable time, sir. We are
Pleasure
looking
to.
forward for your further collaborations.
Hello, Professor.
Hello. Hello.
Thank you so much
Hello.
for your wonderful time and insight towards the talk. It was great speaking with you and great to be a part of this Second International Colloquium. And in future endeavors, also we looking for a great collaboration and also for great insights. Thank you so much for a wonderful session. Thank you so much.
Thank you. Thank you. Have a good day. Bye-bye.
Thank you, Guru Raj, sir. I wholeheartedly thank all the
Thank you.
participants for attending the session. Thank you all.
I hope so. You shared the feedback link there, right?
Yes, sir. It's been shared on the YouTube.
Thank you. Thank you. Thank you.
Thank you, sir.